So this is the first chapter, introductory chapter. I won't go through every single part. Obviously, you can read that on your own. I want to explain you more or less importance and go over the more important aspects of this chapter. So first, this is just introduction. Explains more or less role of chemistry of natural products, what it is, and role and placement of natural products with respect to other disciplines such as organic chemistry and biochemistry. Um, Chemistry of natural products deals with secondary metabolites. So compounds that are products of secondary metabolism, and that's very diverse. Those are often unique biochemical pathways, although sometimes they're common to a number of classes of organisms or organisms. But they are unique pathways, typically unique pathways, as opposed to primary metabolism, general pathways for formation of primary metabolites like carbohydrates or monosaccharides, amino acids, proteins, nucleic acids, fatty acids. That's all primary metabolism, because those are compounds that are common to all the living organisms. So on this scheme, you can see that you see placement of chemistry of natural products within a larger kind of larger group of disciplines. So biochemicals start or have origin in photosynthesis. So from carbon dioxide and water, glucose is synthesized in the course of photosynthesis, and then that leads to synthesis of all other chemicals, and that also may include various chemical modifications, including addition of other elements such as nitrogen, sulfur, phosphorus. So from biochemistry, you're probably familiar with glycolysis. And so glucose undergoes glycolysis. And there are a number of compounds that are intermediates of glycolysis until we end up with pyruvate. So all those intermediates, instead of being used for generating energy, could be drawn into other pathways to produce other biomolecules. In this case, those in purple are various, actually, these are in purple are amino acids. Yeah, this is, I thought it was going to be a bigger, more noticeable difference. Acetyl coenzyme A is in blue because it's not amino acid, but it looks very much like these purple amino acids. So you can see how amino acids are synthesized from products of glycolysis, or phosphoenol pyruvate gives rise to shikimic acid, is used for synthesis of shikimic acid, and that's shikimate pathway, which gives rise to aromatic amino acids. All those amino acids are precursors of number of secondary metabolites, mainly alkaloids, but also some others. Other important pathway is acetyl coenzyme A pathway, and that one leads to formation of oxaloacetic acid, which then results in formation of other other amino acids, or also acetyl coenzyme A could be used to form polyketides, which we'll be studying later in this course. To us at this time, the most important pathway is mevalonate pathway. And even though mevalonic acid is synthesized from acetyl coenzyme A, this is completely different, completely independent pathway. And that one results in synthesis of terpenes, terpenoids, and steroids. Now, I may have to remove one of them or put maybe terpenoids in parentheses. In older literature, terpenes and terpenoids were kind of distinguished from each other. The terpenes were direct result of synthesis from isoprenoid units, while terpenoids were chemically modified. Now, actually, that's changed, and we use term terpenoids for terpenes, and we avoid using the word terpenes. I'm still sticking at the moment with word terpenes, but probably I will have to change that. Both are being in use now. So this distinction, terpenes versus terpenoids, is no longer operative. And there are steroids, which we'll be studying in a separate chapter. They are derivatives of terpenes. Now, here are some concepts that are going to be very important in your course. We have covered them earlier in organic chemistry, and you need to review them so that you can follow the course. So what are stereoselective and stereospecific reactions? So that's explained here. This is part of organic chemistry you already covered. So make sure that you read this, that you know what are stereospecific, stereoselective reactions, and so that you can recognize them when you see them. And then another important aspect is chirality. A lot of biomolecules, particularly secondary metabolites, are chiral, and their properties and biological activity in particular depends on which isomer it is. So it depends on their chirality. And that's again something that you are familiar with. So as you can see here in detail, we are going over chirality. So again, as I said, review it if you forgot this part. Separation of enantiomers is something we did not cover in organic chemistry course, but it is in the book. And now it may be important because now it is of practical importance because in case chemistry of natural products, as needed, we separate enantiomers. So you may need to know how it's done. And then finally, very important concept of prochirality. That's something new. That's something that we usually don't cover in introductory organic chemistry course. So prochirality or prochiral centers are centers that themselves are not chiral because they have two identical substituents. But remaining two substituents are different. They are different from the first two, and they are different from each other. So a typical prochiral center is carbon with three different substituents. So two are identical, but overall there are three different substituents. So those two identical substituents are actually topologically non-equivalent. They're also called heterotopic. They could be enantiotopic or diastereotopic. They're non-equivalent because replacement of one of them with another fourth substituent results in formation of enantiomer, chiral compound. And replacement of each of them in turn results in formation of pair of enantiomers. So we identify those as pro-R and pro-S substituents. And you should be able to distinguish, including distinguishing on the test, which substituent is pro-R and which one is pro-S. Simply, you look what happens if we replace it with higher priority substituent. So on this carbon, you're considering oxygen, that's priority 1. Carbon, priority 2. And then these two are same priority, priority 3. But if we replace one of them with higher priority, then that one will be 3 and hydrogen remains priority 4. So if this is priority 3, if this is replaced with higher priority substituent, we will assume it's 3, not 1 or 2, but just higher priority than the other identical substituent. Then this would be R enantiomer. And so this is pro-R hydrogen. If we replace other hydrogen with higher priority substituent, priority 3, then this would be S enantiomer. So this is pro-S. And so that's how you distinguish two hydrogens, pro-R and pro-S. On their own, they are indistinguishable. In NMR spectrum, they give only one signal. But with chiral enzymes, they often react differently, and enzyme may specifically remove one and not the other. So remove pro-R or pro-S. We figured that out. For example, in this particular case of ethanol, enzyme alcohol dehydrogenase removes only pro-R hydrogen and leaves pro-S in the product. The way we know that is, of course, we wouldn't, just by using alcohol, we wouldn't know that. We couldn't, that wouldn't tell us anything because one hydrogen is removed, one remains. We wouldn't know which is which. But what we do is we replace one hydrogen with isotope. We use either deuterium, and so that's easily observed in NMR spectroscopy, or we can use tritium, which is radioactive, and so that's another way to do it, more expensive. And so when we use deuterium and place deuterium in pro-R position, resulting acetaldehyde contains no deuterium. If we place deuterium in pro-S position, resulting acetaldehyde contains 100% deuterium. So that's an indication that pro-R is removed and pro-S retained. So that's how we know. And so these two hydrogens are enantiotopic. On the other hand, if there is chirality center elsewhere in the molecule, then the molecule is already chiral. And if we have two heterotopic substituents like these, then replacement of each with higher priority substituent will give us two diastereomers. So for that reason, these hydrogens are called diastereotopic. And there is fundamental difference between enantiotopic and diastereotopic hydrogens, because diastereotopic hydrogens are actually chemically different, and because they are surrounded by different substituents. And so they actually react differently both with chiral and the achiral reagents. And also they give different signals in NMR spectra. So such CH2 group that is diastereotopic will give two signals, one for each hydrogen. And those two hydrogens will be coupled to each other. Let me briefly stop sharing. Okay, so are there any questions? I used to have option for a chat. I didn't use it in a while. Trying to figure out where it is. No, I don't see it. Okay. I was going to ask you to type question in a chat, but I can't see it. Okay, let's just go back to the lecture. Besides prochiral substituents, which are usually hydrogens, but not always, we also have prochiral phases. So if carbon is trigonal planar, if it has double bond, then it has two prochiral phases if all three substituents on carbon are different. And so addition from one phase would result in formation of R enantiomer, in other S. But in this case, we designate phases in much easier way. Basically, what we do is we look at phase straight on. So we place three substituents right in front of us, and then look at that phase. What is the array of the three substituents? What is the order of priority? So 1, 2, 3. If it's clockwise, then it's Re phase, and if it's counterclockwise, Psi phase. And so each trigonal planar carbon has two phases, Re and Psi. And again, enzymes distinguish between the two phases and will selectively add from one phase or the other. That's if carbon is bonded to substituent like oxygen, nitrogen, sulfur with a double bond. If two carbons are bonded to each other, then each carbon has its own Re and Psi phase. And then it depends how reaction works, whether both carbons end up being chiral or not, then we will say addition occurs to Re or Psi phase. So in this case, to butene, you can see on one side, one carbon has Re phase, the other carbon has Psi, and on the other, the opposite. Example is citric acid cycle. So fumaric acid is converted to L-malic acid, and enzyme is fumarase. Now we have two Re phases and two Psi phases. Addition occurs from Psi phase, but we are considering only this carbon to which addition of hydroxyl group occurs. And so we would say in this case, if these were two different phases, like Psi and Re, and then Re and Psi, we would say addition occurs to Psi because that's where new chirality center is. We ignore the other carbon, even though that one has two phases, because that's not new chirality center. We have two hydrogens. If both end up being chirality centers, then we have to specify both phases to which addition occurs. Okay, so are there any questions?